Good afternoon, folks. Science and Technologies here at Forsyth Tech, and it's my pleasure to welcome you to our SciTech lecture series today. This has been a really good series for our college and for our students. We've had over 3,215 folks attend about 40 different lectures ranging on all sorts of topics from forensics to HIV treatment. So it's a great series. It started over a couple of cups of coffee, from what I understand, before I was here. Dr. Davis there runs something called Divisional Coffee every morning, and a lot of faculty will get together and talk about ideas to improve student learning. And this series was born. Rick Mutton was part of that, and it's been a pleasure to attend these different lectures over the past few years, and I've learned a lot, and I know our students and faculty have. Today's speaker is one of our own faculty, and I look forward to learning more about his travels, but I'm not going to introduce him. I'm going to ask his department chair to come up and introduce him. Department chair is Dr. Dwayne Leprechaun Davis.
Well, it is St. Patty's Day. When they asked me to introduce Travis, I really didn't know quite all I would say. But in looking at his resume here, I would say that I would be just as well to say Bond, James Bond. Travis has done a lot of traveling, done a lot of things, and Travis is a good example of something that my first supervisor out of college told me. We were trying to hire people for our company, and he said, when you find someone who's qualified and they're a good person, you better hire them right now. And I have several examples of people in here that are in my department that applies to. We hired them, but if you know anything about our HR department, we never hire anybody right now. But let's talk about Travis here for just a second. Travis got a BS in biology and a BA in chemistry from High Point University. And while Travis was at High Point University, he actually did undergraduate research on a biological topic, which I'm not going to try to pronounce. Like I said, it's St. Patty's Day. But after attending High Point University and graduating with some honors, he attended the University of North Carolina at Greensboro, where he obtained a master's in biology. And his research was in myosin heavy chain kinase D protein in the model organism, like a dye something. I'll let him talk about that. But it was a very good research project. And after he completed that, he went on to get his doctorate in medicinal biochemistry. And in that research, he did research in the effects of tobacco smoke on human T cells, which is a very fascinating research. And he's taught for many years. He taught while he was at UNCG for me and for them. And he notes here that he has traveled to 6 continents, and he's seen 6 of the 7 wonders of the world, and that he enjoys fast cars and working on his Aston Martin Vantage. So, with no further ado, Dr. Travis Russell.
Thank you. The organism he was trying to pronounce was Discoidium, Dictyostelium discoidium. It's a slime mold, all right? Very interesting stuff, right? Slime molds, very interesting. That was a joke. So what I'd like to talk about today is a trip I took last year, May of last summer, I got the opportunity to go to Ukraine and visit the Chernobyl power plant. There was lots of governmental red tape, but it took just about a year to get through everything, but finally was able to get the okay and took this little trip last summer. All right, so the way I would like to structure this talk is first I want to talk about what happened. All right, so we're all on the same page, what happened in 1986. And then I'll go over a little bit more about my own trip and show you some photos that I took. And then finally I'll end with what's actually going on now and plan for the future to try and fix what happened 30 years ago. All right, so what happened? Well, let's back up a little further and let's make sure we all understand how we take, how we get nuclear energy, all right? How do we take a nuclear compound and turn it into something that whenever we flip the switch, the lights come on, all right? And the way this happens is through a process called nuclear fission, all right? In nuclear fission, we have a heavy metal, unstable nucleus. In nuclear reactors, that tends to be uranium-235, all right? This uranium-235 nucleus here, it's already unstable. Whenever this neutron bombards, this neutron collides with that nucleus, you get a reaction, all right? In this reaction, you get splitting of that large nucleus into two smaller nuclei. In addition to these smaller nuclei, we get some thermal energy, all right? So this is the key to nuclear reactors. Now the key to causing this reaction over and over and over again, causing a chain reaction, is the fact that we get these three neutrons produced in the process of this nuclear fission reaction. All right? Nuclear fission, not to be confused with nuclear fusion. Nuclear fusion, you take two smaller nuclei, make one big one. All right? Nuclear fission is what occurs in nuclear reactors. So with the production of these three neutrons, we can collide with three new nuclei, right? We can produce three more fission reactions. Then we get 9 more nuclei, or neutrons. We can collide with 9 more nuclei, all right? So this is where the chain reaction occurs. Now, how do we turn that thermal energy from this reaction into electricity? This is just the general basic idea of a nuclear reactor. The reaction occurs here in the reactor core, all right? So this is where the fission reaction is happening. We have liquid water, some type of coolant, that's moving into the reactor core. That water is taking that thermal energy. It's going from liquid to steam, okay? That liquid, or that steam, is then shuttled to a steam turbine, which turns, all right? Then we take the mechanical energy of that steam turbine turning, we turn an electrical generator. That generator turns, produces electricity. So we're taking thermal energy, converting to mechanical energy, converting to electrical energy, all right? All right, so now let's go to Chernobyl. Chernobyl is located in current-day Ukraine. It's about 70 miles north of the capital city, Kiev, and it's probably about 10 miles away from the Belarus border, all right? This power plant was constructed in 1970. At the time of the accident, it had 4 reactors, all right? The first one also being built in 1970. The city of Pripyat, that is a city that borders or is right next to the reactor. This is the city that was also built in the 1970 to house the workers that were building the reactors, as well as to house the individuals working at the reactor once it was built and up and running. All right, and at the height of the plant, when all 4 reactors were working, it supplied about 10% of all of Ukraine's power. Okay, so now we go to the specific type of reactor that the reactors that were built at Chernobyl. And these are called RBMK1000 reactors. All right. Here we have the Russian interpretation of where that RBMK comes from. I'm not going to try and pronounce it. All right. The 1000, that refers to the fact that this particular reactor would produce 1,000 megawatts of energy. All right. So now let's look inside the reactor. Let's see how this reactor works. All right. Because this will be crucial when we talk about the accident, what actually happened. All right. So here, the very center, we have the reactor core. All right. The reactor core has graphite moderators. So this gray area here on the sides, as well as in the middle, this is graphite material. It's a moderator. A moderator in nuclear reactors, what it does is it takes those neutrons that are ejected in the fission reaction and slows them down. All right. This is important because when it slows down those neutrons, they have a higher likelihood of colliding with another nucleus, all right, causing that chain reaction. So the graphite moderator is on the outskirts as well as inside. Inside the core, you'll see these yellow rods. Those yellow rods are the actual fuel rods. So that's the uranium-235. And that's where the fission reactions are occurring. Also, you will see these black rods coming from the top and the bottom. Those are control rods. Okay, so the control rods are required in order to keep these fission reactions under control. The control rods in this particular type of reactor were made out of boron chloride. Boron chloride is an acceptor, an absorber of neutrons. All right, so the way they would control these reactions is by altering how high or how far into the reactor core these control rods were placed. All right, the further out those rods were, more fission reactions were occurring, more thermal energy, more steam, more power. All right, as you insert the control rods into the reactor, you start to absorb some of those neutrons, so therefore you have lower power levels. All right, and it's important to note that these control rods had graphite tips. All right, that'll be important when we get to actually what happened in the accident. Remember what the purpose of that graphite is. The control rods had graphite tips. All right, so we have water being pumped in from underneath, from the lower side of the reactor, into the core. Thermal energy exchanges with the water, producing steam. All right, that steam is then pumped out to 3 different steam turbines, which then power this electricity generator, producing the electricity. The steam is then condensed back down to liquid water, and the process happens all over again. All right, so this is the basic function of the particular type of reactors that were built in Chernobyl. All right, as I've already mentioned, Chernobyl had a total of 4 power plants, 4 reactors. There were 2 in the process of being built, 2 extras, 5 and 6, being built at the time of the accident. They were never completed. After the accident, they just stopped working on those. Reactor number 4, which is where the accident occurred, was completed in 1983. All right, so 13 years after starting on the plant, they built reactor number 4. So what's wrong with this particular type of reactor? This RBMK1000 reactor was Soviet designed, and it was only built in the Soviet Union. All right. Now there were some inherent complications, some problems with this particular type of reactor. Number one, they didn't have a containment structure. All right. All 3 of these points are very important in what actually happened in April of 1986. But there was no containment structure. Why? Cost a lot of money. All right. If we can reduce that cost, then the power that's produced costs less. All right. These containment structures are very thick concrete, steel, lead. All right. So in order to save money, there was no containment structure in any of these types of reactors. In addition to no containment structure, they had a high positive void coefficient. So what a void coefficient is in terms of nuclear reactors, it's how the reactor reacts to the formation of steam from liquid water, okay? So you gotta think, liquid water is a very dense material, very dense. So that liquid water will help in absorbing some of those neutrons that are produced in the fission reaction. But whenever that water is turned into steam, steam is about 1,700 times less dense than water. So the less dense steam will not absorb any neutrons, all right? So what happens when the reactor turns the water to steam is known as the void coefficient. A positive void coefficient means whenever you turn the water into steam, you increase the power. A negative void coefficient would be you decrease the power. A zero coefficient is what's normally wanted, all right? Means there's not really a change in power whenever you produce that steam. But this particular type of reactor had a high positive void coefficient. In addition to the high positive void coefficient, this type of reactor is very unstable at low power levels, all right? The reason for that is also because of the high void coefficient, but at very low power levels, you have to decrease the amount of water being pumped into the reactor, all right? If you want to produce steam, you have to decrease the amount of water, all right? At low powers, if you keep a lot of water going through, you're not going to produce any steam, meaning you're not going to produce any electricity. So at low power levels, they had to reduce the amount of water produced. Because of the high void coefficient, whenever you reduce that water pumping into the core, you increase the power levels. You make it very unstable, all right? So this type of reactor, very unstable at low power levels. So reactor number 4, like I said, it was completed in 1983. All the safety certifications were signed in 1983. The test that was being done in 1986 should have been completed in 1983 before the reactor ever came online. Papers were signed when they shouldn't have been. And the test that they were actually trying to complete in 1986 was to ensure that they didn't lose power to the reactor, all right? This is a big concern in any nuclear reactor anywhere in the world, is loss of power to the plant, all right? If you lose power to the plant, you lose power to these circulation pumps. The circulation pumps are what are pumping water into the reactor core. If you lose power to the pumps, you lose coolant. Then you get a meltdown, all right? So it's very important to make sure you have backup power in the event that you lose power to the plant. Now, most nuclear reactors have a backup power source, being a diesel generator or multiple diesel generators. The issue with having a diesel generator as backup power is it takes between a minute to a minute and a half for that generator to spin up to provide enough energy to the circulation pumps. So there's something is needed to bridge that gap between whenever the power goes out of the plant to the point minute and a half later where the diesel generators can pick up providing power to the pumps, all right? And the test that was being done, that was being conducted in April of '86 was to try and bridge that gap. What they were figuring was what we can do, all right, whenever the power goes out at the plant, those steam turbines are constantly moving around. They're still spinning, all right? Whenever the power goes out, they're still turning. So can we use that inertia of those spinning steam turbines to spin the generators to provide enough electricity to bridge that minute and a half gap, all right? So that was the test. That's what they were trying to do. All right, so now what I'm going to do is I'm going to take you kind of time by time, second by second, as to what happened on April the 26th, all right? It all started April the 25th of 1986. It was a Friday. This is when the test was planned to be conducted during the day shift, all right? That's important. The day shift crew, they're the most experienced all right? They had all been briefed on how the test was going to go. There were engineers present to ensure there was enough electricity going to the pumps, enough water being pumped through the reactor. Everything was set up. Everything was good to go. So about 1 o'clock on Friday afternoon, they started to reduce the power in the reactor, reactor number 4. The reason for reducing the power, the test parameters said the power needs to be somewhere between 700 and 800 megawatts. All right, so they started to reduce the power to get down to that power level. The issue was, back in Kiev, in a different power station, there was a loss of power somewhere. All right, so the grid controller in Kiev phoned up Chernobyl, said, hey, can you postpone this test for a little bit? Because it's Friday afternoon, right? Friday, lots of power usage in the afternoons, people getting off work, people going home. Due to this loss of power from somewhere else, they decided to postpone the test. All right, we're going to postpone it, see if we can get power back from wherever it was lost. And they were able to regain the power. So about 11 o'clock that night, say, all right, you're good to go for the test. So at this point, the day shift, gone, right? Gone home. The engineers also gone. At this point, we've got the night shift, third shift individuals. These are the people that are the rookies, not as experienced as the day shift. So midnight, now we're Saturday morning, they started to bring the reactor power down again. At about midnight, power reached 700 megawatts. The issue was somebody inadvertently inserted those control rods a little bit too far. So the power not only got to 700, but continued to go down. They knew the power needed to be up somewhere around 700 in order to conduct this test. So what do? We remove control rods, all right? In order to remove the control rods, they had to disable the safety system. Problem, right? Don't disable the safety systems. They disabled the safety system to pull out almost all of the control rods. And power started to increase back. Got up to about 200 megawatt. About 1 a.m., they had to turn on some extra water pumps. All right, this was part of the test parameters. So they need a lot of steam. They want those steam turbines to be spinning whenever they start the test. So they add more water to the core, make more steam. Well, you add extra coolant to the core, you're actually going to decrease the power level, right? Because there's more coolant, all right? So there's less steam. So what do they do to increase the power? Remove more control rods. At this point, there are only 18 of the 211 control rods in the core at this point. So, time to start the test. About 1:23, the test was started. So in order to start the test, they had to remove steam going to the turbines. All right. Then they diverted the power that was operating the circulation pumps to the generator from those run-down turbines. All right. So the turbines now, they have no steam. They are starting to slow down. And the power that's coming from those turbines is now powering the pumps, pumping water into the core. As that turbine starts to slow down, less power is produced. Less power produced, less water being pumped into the core. This causes the temperature within the core to increase. Not, 36 seconds later, after they started the test, the emergency scram procedure was initiated. There is some debate as to whether this was computer initiated, or manually initiated. From what I can tell, I think it was it was manually done. To manually start this scram procedure, there's a button called an AZ5 button. This is a photo of the control room inside of reactor number 2. All right, this is not reactor number 4. It would look the same, but in order to get into reactor number 4, A lot of extra paperwork. All right, so we weren't able to go inside of reactor 4. We were in reactor number 2. So this is the control room of reactor 2. Once again, this second button here from the left is the scram button. This immediately inserts all control rods. Okay? But the problem is those control rods, they have graphite tips. What does the graphite do? It moderates the neutrons rather than absorbs the neutrons. Moderate the neutrons. As soon as those control rods were inserted, there was a massive power spike. All right. The reactor that's designed to produce around 1,000 megawatts, power spike, the very last value on the control panel, 33,000 megawatts. So this causes explosion number 1. Explosion number 1 was due to steam buildup. Here you'll see a cutout of the reactor. This steam explosion, high pressure steam inside the reactor core, it blew this 2,000-ton biological shield. So this is not a containment. Remember, this reactor has no containment structure, but it does have a biological shield. I have a picture later on of what that shield looks like, but it's just a 2,000-ton piece of steel and lead, all right? Something has to protect the workers whenever they're going in and replacing the fuel rods, replacing the control rods, all right? So they had this big metal plate right here, which is supposed to be over top the reactor. There's one over top the core and one underneath the core. The steam blew that top plate completely off. It hit the roof, went through the roof, turned, fell back down onto the reactor, and this is what you see here. So this is the plate turned 90 degrees. All right, this plate here turns 90 degrees where all these pipes should be going into the core. All right, so it blew this plate completely off the reactor, fell back down on top of the reactor. At this point, you've lowered the pressure inside the reactor. Okay, when you lower pressure inside the reactor, you cause what any liquid water that's present to immediately flash into steam. So at this point, we have no coolant. These are some photos taken a few days after the accident. You'll see here, this is a picture of inside the reactor core. This is that 2,000-ton plate that was blown into the air. And you'll see here, this is the reactor building. The entire roof, pretty much, the entire roof is completely gone. So, like I said, we've lowered the pressure inside the core. All of the water has flashed to steam. There's no coolant now. The graphite moderator, it's superheated, all right? It's inside the reactor core. As soon as it comes into contact with air, it bursts into flames, all right? This is what caused most of the radioactive fallout in the surrounding areas. You'll see here a map of the fallout levels where they went. You'll see right here in the area of the plant, we have somewhere between 40 and 100 times normal levels of radiation. Here, this is a valve underneath the reactor. You'll see this, what looks almost like lava flowing out. This is called corium. Corium is essentially lava. It's made up of fuel rods. It's made up of melted moderator, graphite core. It's made up of iron, steel, whatever was in the path. This photo here was taken by a robot. Any human that would have been this close would have received a lethal dose at that time. So the second explosion, about 2 to 3 seconds after the first, and it caused a fire, that graphite moderator, which is what spread all of the fallout. So what happens after the explosion? Initially, the individuals inside the control room had no idea anything had even happened, all right? They were under the impression there was no issue. They heard a small boom. They went to find out what happened. It took 24 hours before they ordered the evacuation of the nearby town of Pripyat. It only took 3 to 4 hours before people started experiencing symptoms of acute radiation poisoning, being metal taste in their mouth, vomiting, severe headaches. But this 24 hours that it took before they ordered the evacuation, this is what caused a number of the defects and the radiation poisoning of the individuals in that town. They were initially told whenever they were evacuating that it would last approximately 3 days. So if you were told that you're leaving your house for about 3 days, you're going to take your personal possessions, all of that? No. All they took was some clothes, maybe some food. Some even left their pets behind. All right? 48 hours after the explosion, the evacuation zone was expanded to 10 kilometers from the reactor. And about 10 days after that, it was expanded to 30 kilometers. That 30-kilometer exclusion zone is still in place today. 30 years later, 30 kilometers from the reactor, you're not allowed to go in closer than that. So now I want to kind of switch to current day. All right, so I'll talk a little bit about my personal trip. The trip started, I started planning for the trip in about, it was May of 2014. Most of you probably remember the Ukrainian Revolution that occurred in February of 2014. It stemmed from the president of Ukraine deciding to sign a deal with Russia versus the European Union. Most of the population wanted to go with the European Union, and from what I understand, the president was intending to go with the European Union, and at the very last second, he decided to sign with Russia. So this caused mass protest this is Kiev. This is known as Independence Square, or Maidan Square. So during this protest, the president orders the military to come in and remove all of the protesters. It got very violent in February, somewhere between, I believe, 70 to 100 deaths during this revolution. It ended with the president being run out of the country to Russia, and eventually they ended up signing back with the European Union. This is also the cause of Russia's invasion of the Crimean Peninsula. So whenever the president signed with Russia, and they kind of went back, Ukraine went back on their deal, Russia did not recognize that, and that's what led to the most recent invasion of the peninsula. So this is what Independence Square looked like after the revolution. You'll see the difference here. The reason I bring this up was because this was just a couple months after I started planning. You'll notice this building here in the background. This is Ukraine Hotel. This is where I actually stayed for 3 days before going up to Chernobyl. So these are some of my photos. You'll see here, this is May 2015. The square looks a lot different than it did in 2014. All right, there's a memorial here for those that died in the revolution. This is a view from our hotel room balcony. And now we're going to go to Chernobyl. All right, the first place we come to is the city of Chernobyl. The city of Chernobyl is probably 25 kilometers from the actual plant, all right? So the city of Pripyat is much closer to the plant than the actual city of Chernobyl. So we enter at the 30-kilometer exclusion zone. This is about the best picture I could get of the exclusion zone. It's military run, so they don't allow any pictures to be taken. So this is about as close as I got. Once we got through the checkpoint, we come to the entrance to the city of Chernobyl. All right, did anyone know that you could actually have a Geiger counter, a personal Geiger counter that works with your phone? It's called a smart Geiger. This fits right in your phone. Anybody can buy one. I actually purchased one before I went. We were given a Geiger counter by the government to use while we were within the zone, but I had two. This is the reading levels at the 30-kilometer checkpoint. All right, so this is 0.3 microsieverts per hour. Give you some kind of comparison, a lethal dose is about 0.9 sieverts per hour. First place, the city of Chernobyl, all right? This is where there's the memorial to the firemen who died during the accident trying to put out the fire within the core. And we come to the robot graveyard. After the explosion occurred, before they built a sarcophagus over the reactor core, they had to try and get all of the reactive material back inside the core. So an explosion caused some to go out. They needed to try and get it back into the core before they built this sarcophagus. Initially, they tried to use robots to do this. The issue was the radiation was so high, the robots went dead a few minutes after starting up or getting close. So after this, they had to use what they called biorobots. In other words, humans. The humans were mostly military members, all right? They were allowed to go out on the roof, shovel material back into the reactor core for approximately 10 to 15 seconds. And even in 10 to 15 seconds, some of them got lethal doses of radiation. All right, so continuing on closer to the reactor, we come to the 10-kilometer exclusion zone, similar to the 30-kilometer checkpoint. Here you'll see what remains of reactors 5 and 6 that were in the process of being built when the accident occurred. And here we have the first view of reactor number 4, and you can see the Geiger counter says now the readings are going up slightly, 1.4 microsieverts per hour. Now before we actually got to reactor 4, we stopped off at a bridge. There was a railroad bridge over a stream of water right there next to the reactor, and we took some bread with us to feed the fish. After about a minute and a half of feeding these smaller fish, we started to get these giant catfish. All right, to give you some bit of reference, these fish are probably 2 feet long. So we're looking at probably 10 to 12 feet long catfish in that area. There's different views on this. Are they mutated because of the radiation? Probably not. Probably the more reasonable, the reason why they're so large is because there are no humans. There are no humans nearby, so there's nobody to catch the catfish. Then we get to the reactor. This is the monument to those who saved the world. That's what it's called, with the reactor number 4 in the background. You'll notice here, this is the sarcophagus that I told you about that they built after getting all of the radioactive materials inside. You'll see some of the workers here. These are workers who are currently completing the new safe confinement that's being built to try and remedy what's happened. Moving into reactor number 2, here we have the hall going to the control room. The control room itself, you'll see there are some scientists there. They were doing something that day. We didn't know, we didn't ask. AZ5 button, once again, some other photos from the control room. Here is that biological shield I was telling you about. So this is reactor number 2. Nothing wrong. You can see the size, these people, these guys inside. This is the 2,000-ton biological shield that was blown off the reactor in that first explosion. You'll notice each one of these little tiny blocks within this shield, these are individual spots where they could remove fuel rods and replace the fuel rods or replace control rods if needed. After the control room, we moved over to the circulation pump hall and the turbine hall. So this is a photo you've already seen, the circulation pumps. And here is the turbine hall. So these are those steam turbines that the test was being completed on for reactor number 2. After leaving reactor number 2, we left out and went to the city of Pripyat. All right, so here we have the city sign. This area is known to have some of the highest radiation levels. because of the way the wind was blowing whenever the accident occurred. You'll see here, I don't know if you can quite see that. That's 15.2 microsieverts per hour, so still rising. Then we went into a school in the city of Pripyat. All of these are photos from within the school auditorium. Here you see a lot of books strewn about. Still inside the school, we have a gymnasium. One of the schoolrooms was used to place all of the used gas masks that the workers had used. So all over the floor you see just used gas mask all over. Thought it was a little ironic. I noticed one of the posters in one of the classrooms is an anti-atom, anti-atomic war poster. Then we moved out to the amusement park. So this amusement park was being completed. It was set to open the weekend that this accident occurred. So nobody ever got to go to the amusement park. You'll see the Ferris wheel, some of the bumper cars, and look at the radiation levels. These are some of the highest levels that we saw, 81.45 microsieverts per hour there. The community center, so there was a swimming pool which we went down into, and another gymnasium there. And then we left. So before you leave, you have to have a full body radiation check. If there are levels that are unacceptable, you get an extended stay, all right, in the area. They will scrub your clothes, your pants, your shoes, whatever, wherever the high reading is coming from. Luckily, I didn't have any issues, in and out. All right, so then finally I want to move to what's actually happening now. What's in the plans for the future? How are they going to fix what's happened? The current concrete sarcophagus that they built over the reactor was built just the next month after the accident in May of '86. It was designed to last approximately 20 years. Still there now, 30 years later. All right, so something has to be done pretty soon. And so 2003, this new project was announced where they were building what's called the new safe confinement. All right, it was built off-site, so it's essentially an arch design. They built it right next to the reactors so as to protect those that are building it from high radiation levels. Whenever it's completed, it will be pushed over top of the reactor core. The original cost was around $750 million. As of 2006, we're looking at a little over $1 billion. As of now, we're closer to $1.5 billion. And the majority of this is funded by you and I. In fact, the guide that we had that day, he said to thank all of you for your country's generosity. So here we have the new safe confinement. Like I said, it's built right next to the reactor, so the reactor is right here in this area. Once it's completed, they'll push it over top of the reactor. Inside, underneath this arch, you have a number of these beams where they will attach robots and cranes, and then they will remotely operate those and try and remove that sarcophagus and eventually get rid of the radioactive materials inside the core. That's the plan. You'll see just how large that arch design is. It was scheduled to be completed in 2015. That was then moved back to 2016. Now we're set for 2017. Who knows if it'll be completed by then or not. And so that's it. I hope that you learned something. I hope that it was somewhat interesting. I'm happy to take any questions if anyone has any.
Thank you, Dr. Russell. We'll see if there's any questions. Any questions from the people in the back?
So are they trying to just, I guess, are they doing a test run on how, Are they doing a test run on how to clean up a failed reactor by doing all this robotics, or is that sort of the typical procedure?
The way they're attempting to clean up, it has to be done this way. So even current day, right now, individuals that are still working on keeping that sarcophagus, so the older building, keeping it up and still able to keep out rainwater, snow, things like that, they can be on the roof no longer than 12 minutes. In 12 minutes, they receive their annual dose of radiation. So after 12 minutes on the roof of that sarcophagus, they can no longer come near the reactor anymore for an entire year. So remotely operating these robots that's what they have to do. There's no other option.
How long will the structure last? How long will the new structure last?
The new one, as long as it takes to try and clean up. I don't think they've set it to last a certain amount of time. They're going to use it to try and get rid of all of the radioactive material inside.
Questions in the back? Yes.
What was the highest level of radiation that you experienced?
So the highest that we measured was there in the amusement park. It was around 81 microsieverts per hour.
81?
81, yeah.
Okay, did you experience any symptoms?
No. So that's still low enough that it shouldn't cause any long-term effects. It's microsieverts, whereas the lethal dose is actually in sieverts, so we're looking at a difference of 1 million there. So no, it's low enough levels that it's all right to go in without any protection.
Questions? Questions? Any questions? Yeah, great. Kirsten. Yeah, but it's for the video. Yeah, sorry. There's a video.
My question is, how close are people currently living near the power plant?
So there were some individuals who decided they were allowed to move back into the city of Chernobyl. No one lives in Pripyat. No one lives within 10 kilometers of the reactor. But after a certain amount of time, they were given the option to move back in the city of Chernobyl. There were some individuals that did move back. They're not supposed to be allowed to grow anything, any food on site. So all food has to come from outside of the containment zone. Whether they're doing that or not, who knows? But there are, I don't know a number, but there are a number of people that did move back in.
So no fishing.
No fishing.
Really?
No fishing.
Wait. Good. Anybody else? Michael? No? No? So why? Why did you choose Chernobyl?
That's a good question. I guess I've always been somewhat interested in nuclear chemistry. And when I had no idea that you were really allowed to go and visit Chernobyl. I'd been doing some research, and I found that if you are in the science background or if you are in a teaching background, that the government will actually allow you to come visit the reactor, go inside of one of the decommissioned reactors nearby. And so that's the route that I went. In fact, anyone can go visit Chernobyl. So there is a new wave of tourism called dark tourism. It's essentially visiting areas of death, right? So going to Chernobyl, going to concentration camps, things like that. So you are allowed. There are tourism companies that will take care of all the paperwork for you, and you just show up to Ukraine and they will take you into Chernobyl and allow you to see. I don't think you get to go inside of the reactor area, but you can at least go around, see the outside and things like that.
Well, it's fantastic. Well, I want to thank you, Travis, on behalf of the college for a great lecture. And as you know, this lecture is being videoed, so we don't know. You'll probably get some reaction from some people living in Chernobyl. Anyways, but before we close, I'd like to ask Dean Ayers to come up to the front of the podium, if he could. And on behalf of the college and on behalf of our trustees and Dr. Green, we'd like to present you with a small token of our appreciation for your, and by the way, Rick Mutton and Dwayne, would you please come up as well? So I think this one, Travis, is for you. That's Dwayne? Sorry, you want to hold it? I can't see that. Can't. Let me see now. This one's for you, Rick. Come on over. Okay, and we'll explain these in a minute. And Travis, this is for you for today.
Thank you.
On behalf. So let me explain these. As Dean Ayers said in his opening, that we've had 40 lectures and approximately 3,250 people come to these, and you are the audience who have come, and we know you like these lectures. And so we aim to continue. But I think in good conscience, Dean Ayers and myself sat down and we thought about it, and we said, you know, the people who invent things need to be recognized for their innovation. And so for Rick Mutton and for Dwayne Davis, this is in honor of your invention.
Thank you.
Which is SciTech. And for those of you who have an opportunity and you want to see every SciTech that's ever been done, there is a flip book at biotechworkforce.org. That's the National Center's website, and you can actually go there and you can flip through all the speakers for the last 6 years that we've had. So, Rick, welcome back.
Thank you.
And I'll give the last word to Dean Ayers.
Well, thank you all for coming. I think I want to visit Chernobyl. That sounds, but I'm also a cat fisherman, so the thought of a 10-foot catfish is pretty cool. Thank you both for your invention. Thanks, Dr. Russell, for a great talk. And Russ, thank you and your staff for putting this together. This is a really good series, and we look forward to it, as you said. All right, so everybody have a good afternoon. Thank you for coming.